All right, so let's see here. So I want to just pause and see. Yeah, so I probably should just erase these things, but you know, it's probably worth me just taking a second to share some linear algebra with you. Famous last words. So when a matrix has enough eigenvectors that if you have an n by n matrix that has n eigenvectors, all right. Here's the basic theorem. If we have P is equal to like U1, U2, UN, where A Uj equals to lambda j Uj, for j equals to 1, 2, all the way out to n. And the determinant of P is not equal to 0. In other words, I'm saying that you actually have n linearly independent eigenvectors. You can put them together and then make an invertible matrix. The cool thing is you can show then that P inverse AP is a diagonal matrix. And its diagonals are the eigenvalues, lambda 1, lambda 2, lambda n. In other words, A is diagonalizable. A matrix is diagonalizable if a similarity transformation, really a coordinate change of sorts, can make the matrix turn into a diagonal matrix. Not all matrices allow this, but when it does, it's precious and special and nice. And those kinds of matrices, the solutions I've been showing you so far, will fill out the general solution. There's something even nicer, though, which is called the real spectral theorem. The real spectral theorem, and this is Dr. Scombordis' fault for getting me thinking about this. Real spectral theorem. I mean, he was mostly telling me it to not tell you guys, but I kind of react the opposite way when somebody says something like that. It's in my nature. And it's very simple. It's very simple. It's very easy to understand. It's not so easy to prove. But it simply says this. If we have that A is equal to A transpose, all right? If you have a symmetric matrix, it's the case, if and only if, there exists an orthonormal eigenbasis. Orthonormal means that P inverse is actually equal to P transpose. So for the matrix, that's what it means. It means that the vectors can be arranged to be perpendicular, mutually perpendicular, and all length 1, which is a wonderful kind of basis. It's the one we're familiar with, like a Cartesian coordinate system. There exists an orthonormal eigenbasis, and P transpose AP is that lambda 1, lambda n. There's even more to it than that, but that's enough. I mean, so symmetric matrices are really nice because if you have a symmetric matrix, that means that you can tell before you do any calculation that the eigenvalues are going to be real and that you're going to have enough eigenvectors to form the general solution to your system. So the one I just erased here was a symmetric matrix. 0, 1, 1, 1, 0, 1, 1, 1, 0. If you take the transpose of that, you get back where you started. So that's why we found real eigenvalues for that. Now, this was not an orthonormal basis because I didn't normalize it to length 1, and these aren't perpendicular. But you could run something called Gram-Schmidt and make it orthonormal. All right, enough about that. So if you want to know more about that, you could maybe take Math 221. We do some of that in there, depending on who you have and how the semester goes. I know that saying these things is certainly on Dr. Smith's bucket list for the course, for sure. If I teach the course, I will say these things in more detail with examples. I try to prove this in 321 these days. but it's a hard row. It's not easy to prove. It takes me a while. Okay, enough about that. So, I just think it's a pretty low-hanging observation. You can kind of know where you're going. If your matrix is symmetric, you're going to find real eigenvalues. That's a useful, simple thing for you to look for in examples. And symmetric systems appear in models that are interesting physically as well. So it's not just a math comment. Where are we? Okay, so complex solutions. All right. If you think about it, the determinant of A minus lambda I equals to 0 could have complex zeros, right? So what do we do with those? So first of all, let me just put us on the right path. Fundamental theorem: if dz dt is equal to az, where z is equal to x plus iy, then we have dx dt equals to ax, and we have that dy dt is equal to ay. I think the proof is worth a minute of our time. So let's see here. How do we differentiate a complex vector? I mean, I didn't really define it for you, did I? But you probably already know. We just differentiate the real part and the imaginary part separately. Same for vectors as it was for scalars. All right. One side of the calculation. But the other side of the calculation, if we have A times Z, then properties of matrix multiplication, matrix column vector multiplication, this is AX. We can pull the I out, right? I do need a little bit more fine print here, guys, and this is sort of usually assumed by people who write things like this, but I'm assuming that X and Y, these are themselves both real vectors. That's necessary so that I make sure that there's not some I part in the X or something, right? Once you have all this, then if we have dz dt is equal to az, we can equate these vector equations. We get that this piece has to equal that piece, because that's the real part of the equation, and this part has to be equal to that part, because that's the imaginary component of the equation. So from one complex vector solution, we get, guess what, 2 real vector solutions. You're like, you already showed us this. That is true, but there were no vectors last time I showed you. It was just for a linear differential equation. And it wasn't a first order differential equation, it was an nth order differential equation. But the song remains the same, right? I mean, it's the same song and dance. All right. So you won't be surprised when I tell you. So z equals to e to the lambda t u is a complex solution when lambda is equal to alpha plus I beta, with beta not equal to 0, right? And the real and imaginary parts of that are going to be the solutions that we want, stemming from the eigenvalue lambda. So let's just work that out here before we get into an example. This is kind of standard notation, u equal to a plus ib. So you could say this, the real part of u is A, the imaginary part of u is B. These are both real vectors, okay? So if we calculate z equal to e to the lambda t times u, let's work that out. That's e to the alpha plus I beta times t times u. I would like you to be able to work through what I'm working through right now, but by the same token, I'd also like you to be able to just write it down, the answer, as appropriate, right? If the problem is solve a system, you don't have to go through this all again. You can use it. It's a known result, right? If I say derive known result, then you need to derive the known result. Kind of depends on the instructions for the problem, right? Okay, so here, this is e to the alpha t cosine beta t plus I times the sine of beta t, A plus IB, and then multiply. Let's see here. So all I'm doing, guys, is just grouping together all the pieces without I and all the pieces with I, separating them into the real and imaginary part. I'm also using that I times I is minus 1. That's where that minus comes from in front of the sign. Es bueno. So here's our theorem. If lambda equals to alpha plus I beta has complex eigenvector u equal to A plus IB vector, then x1 equal to e to the alpha t cosine beta ta minus sine beta t b, and x2 e to the alpha t sine beta t a plus cosine beta tb are solutions. Real solutions to dv dt equal to AV. I'm assuming, of course, that that's a complex eigenvector of A. So this is good news. If we find a complex eigenvalue, we get 2 for the price of 1, right? Just like in the previous arc of the course, when we found a complex value for our characteristic equation, we don't just get a sine, we also get a cosine, right? I mean, there's always a pair of real solutions that come with complex eigenvalues. That continues to be true here. Let's work an example. All right. By the way, all these examples are from your book. Where was I? This is example 4, I think. All right, so we're taking the case a equals to minus 1, 2, minus 1, minus 3. Again, just to bring us back to what we're doing, this is x prime equals to minus x plus 2y, and y prime equals to minus x minus 3y. This is a system of first-order coupled differential equations with dependent variables x and y, and independent variable t, which I usually think of as time. All right, so the start of the story is the same. We calculate the characteristic. In fact, this story is really the same, with the extra wrinkle of peeling off from Euler's formula the piece here. So minus 1 minus lambda, 2 minus 1 minus 3 minus lambda. So that's actually lambda plus 1 times lambda plus 3 plus 2. What I've done there is just multiplied the minuses from one to the other. You can verify my signs, yeah? You guys ever see Signs? It's a pretty good movie. Let's see here. Yeah, so that's lambda squared plus 4 lambda, 3 plus 2 plus 5. So here's another opportunity for honing your skills on completing the square. This is lambda plus 2 quantity squared plus 1. So that equals to 0 implies that lambda is minus 2 plus or minus I. Some of you guys are shaky on this algebra. That's part of why you lost points on test 1. You really should try to fix that if you can. That's the place you don't want to lose points because it can be fixed, right? If you're well, anyway, I'll shut up. Okay, so we don't need the plus and the minus. We pick a plus or a minus. I pick a plus. So we're going to pick lambda minus 2 plus I. And so what we got to do is we got to solve a minus 2 plus I times I u, which is what? That's really minus 1 plus 2 minus I, 2 minus 1 minus 3 plus 2 minus I. If we did this right, they should be the same equation. It's not as obvious in the complex case if you're right or wrong, though, right? I mean, for a real 2 by 2 case, it's kind of in your face. If you're wrong, you can kind of see it. Here, it requires a little bit more, like to double check your work. It's a little bit more involved, I think. What we have here is what we've got: 1 minus I, 2 minus 1 minus 1 minus I. It's not entirely apparent to me that these are the same equation. How can you get the second equation from the first? Let's just double check our calculation. These should be the same equation. Otherwise, we only have the solution of 0, right? So this one I can to get from here to here, I do what? I just, rather to get from there to up there to there, what would I do? Multiply by I minus 1, yeah? So what happens when I multiply I minus 1? So notice that I minus 1 times minus 1 minus I is equal to what? Minus I plus 1 minus I squared. What? Oh, I'm fine. I was like, I was getting 0 all of a sudden, but I forgot that minus I squared is actually also known as 1, right? So this is, the i's cancel, 1 plus 1 is 2. Hooray. So what that shows you is if you take the bottom equation and you multiply by I minus 1, you get the top equation, right? So they really are the same equation, even if you don't. Now, if you trust your methods, this, what I just wrote in green is unnecessary, right? This is just, I'm just double checking our work, okay? All right, so getting back on track here, which one of these would you like to use to relate u and v? I personally like the second equation because of this 1, right? Second equation tells me that u is equal to minus 1 minus I times v, right? You got lots of flavor choices here. Like any non-zero complex number you can pick for v. So I'll pick 1. I mean, so yeah, you could do a lot of things here, and so these are really quite awful to grade. But if you guys are lazy and just do what I do, it makes it easier for me. Not that you have to. You can make some weird choice and make my life difficult. I'll grade your paper more carefully then. Sorry. So our eigenvector, complex eigenvector in this case, would then be minus 1 minus I, 1. And so what's the a and b going to be here? Right? So the real part is minus 1, 1. The imaginary part is minus 1, 0. This is a system of, two. This is a second order system, so we have a complex eigenvector, which means we have 2 real solutions, which by the theorem I erased means we're done. We just need to write down the answer, right? So x equals 2, c1, what were we, e to the minus 2t. We got a cosine t, minus 1, 1, minus the sine of t, minus 1, 0, plus c2 e to the minus 2t, sine t, minus 1, 1, plus cosine t, minus 1, 0. There you go. That, my friends, is the vector solution to this problem. I guess I've been using v sometimes for the final answer, but whatever. What are the scalar solutions? X equals to what? Oh, it's quite awful. So C1 e to the minus 2t. Looks like I got a sine t minus cosine t. Plus C2 e to the minus 2t. And minus sine t minus cosine t. And the y, a little bit nicer, C1 e to the minus 2t cosine t plus C2 e to the minus 2t sine t, yeah. So those would be the so-called scalar solutions. Or for some other courses, those would be the expected solutions that a professor would want. Any questions? So why didn't we need to use the 2 minus I? What would the difference have been? Here's the reason for that. If A is real, and if you have A times U equal to lambda U, then if we take the complex conjugate of both sides, I'll use a star for it, since my bars would interfere with my vector notation at the moment. Depending on what you read, complex conjugates either stars or bars, right? So if A is real, then A conjugate is A again, right? It's a matrix of real numbers, so it's fixed under complex conjugation. And then just gives you a complex conjugate of U equals to complex conjugate of the eigenvalue, U complex conjugate. So what this says is that the conjugate eigenvalue has conjugate eigenvector. There's really no new information there, see, because the conjugate eigenvector, if U is A plus IB, then U conjugate is A minus IB. So if you look through the solutions we're constructing here, that just amounts to switching B to minus B, right? So what's that do? It just like multiplies these solutions by a minus 1 or something. I mean, it's the same. They're the same functions if you sort through it. So it suffices to just do one of the eigenvalues, and I usually choose the plus when there's a conjugate pair. That's good. If we somehow found 4 linearly independent solutions, it would be very troubling, because the theorem says there's just 2 to find, right? You guys like another example? How about, let's see here. I'll write down 2 examples. This example, what are we? 5. I'm going to do example 5 and example 6 with technology, if you guys don't mind. I hope you don't mind. So example 5, we're going to look at A equal to 0, 1, 0. It's a 4 by 4 matrix. 0, 0, 1, 0, 0, 0, 0, 1. Minus 2, 2, minus 3, 2. And then for this one, example 6, we're going to look at 0, 1, 1, minus 1, 0, 1, minus 1, minus 1, 0. It's kind of like the one we did earlier today, but with minuses, right? Do you guys remember seeing a matrix like this last time? I mean, yesterday? Is that at all familiar? If we look at a system of differential equations, I mean, if we look at an nth order system, we do reduction of order on it, then we sometimes end up with something like this. Or maybe it's transpose, I forget a little bit. I gotta be careful here. Every once in a while I yank one of these cords, and then like it's got linked over the other one, and you just pull over the little console that's inside here, and that would be like the end of our fun today. So be careful. All right. Come on. Wake up. So this is linked on the place I showed you guys yesterday. I think it's on the differential equations page as well. depending on issues with Java and stuff, I personally always click on the link for the old version of the calculator. You guys are more tech savvy than me, maybe. I mean, you've seen my phone, right? But, so, I mean, the argument could be made that I'm a Luddite. I don't know. Maybe that's true. But if you go back to the original page here, okay, so first of all, this is from my website, yeah? The link I have, where'd that stupid thing go? Links to websites to do the math for you. It's like number 4. Eigenvector calculator, ugly numbers, no problem. I like this one. www.brunner.de, blah, 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 eigenvert. Anyway, so forget all that. Old version of this calculator. That's what I like. And then we got 0, 1, 0. Oop. What's the last row?
-2 to -3.
All right. Well, that's annoying. This is number, let's see here. We're looking at, I think this is number 11 in section 9.6. Let me check on the answer. I'm thinking this could be like square root 2. Oh, wait a minute. Hold on a second here, guys. Something very important that we should notice. You must beware. The problem of finding eigenvectors is numerically unstable. Like, it is a bad numerical problem. So when you ask a computer algebra system to find eigenvectors, it's perilous. Okay, they're theoretically very beautiful, but in terms of numerics, they're kind of bad news. And you can kind of see a little bit of that here. Notice this e to the minus 18. What's this then? That's 0, right? It's machine epsilon. It's a very tiny number. So really, this is just I, ignore, minus I, 1 plus I, 1 minus I. So if we look at the answer, which of course is probably done with pen and paper methods, like we were doing earlier today. Well, marker board and what did I say number was this? Did I say 11? Yeah. Oh, they're giving the answer in the form of the fundamental solution matrix, which I should start talking about, by the way. Yeah, the answer is like exponential times sines and cosines, and then sines and cosines. That's 1 plus or minus I and plus or minus I eigenvalues. Yep. Okay, so, all right, with this, I can then tell you that we have, let's see here. You notice that it gives us like the eigenvalue and its conjugate, so just pick one. I'm going to pick eigenvalue I. So lambda equals to lambda 1 equals to I, and that has u1 equals to, what is it? 1I minus 1I. Right? In other words, 1, 0, minus 1, 0, plus I times 0, 1, 0, 1. Right? So we could think of this as being A1, and this as being B1, right? From the website. And the other eigenvalue, lambda 2, 1 plus I, has u2 equal to, let's see here, 1 plus I. What's the third component? I think that's a 2I. And then the last one is what? It's minus 2 plus 2I. if you can see. And so from that, we can extract the real of 1, 1, 0, minus 2, plus I times 0, 1, 2, 2. So this is what I might call A2, and I'd call this guy over here B2, the real and imaginary parts. And so from that, that's all we need. Now we can write down the general solution. General solution, thus, is C1 cosine t. If you don't mind, rather than writing the vectors out again, I'm going to use the A1 and A1, A2, and B1, B2 notation just to save us some writing here, okay? So C1 cosine t A1 minus sine t B1 plus C2 sine t A1 plus cosine t B1 plus C3 oh, careful. Now this one, I've got 1 plus I, right? So that gives me a e to the t from the 1. And then I've got like cosine t A2 minus sine t B2 plus C4 e to the t sine t A2 plus cosine t B2. All right. Now, I should introduce something. We can write down something called the fundamental solution matrix for any of the systems we've looked at so far. What a fundamental solution matrix simply is X is fundamental solution matrix of dv dt equals to AV, provided two things. Number one, we have to have that dx dt is equal to AX. This condition says that it's a solution matrix. All right? This actually means that every column in X is itself a solution to the differential equation. And number two, that the determinant of X is not equal to 0. These two things put together give us what's called a fundamental solution matrix. So we could write down, one way we could express our answer rather than, well, we could express the possibility of answers by writing down the fundamental solution matrix. Like if I go back to example 4 here, if I go back here to example 4, I can tell you the fundamental solution matrix for example 4 would be, it's unpleasant. E to the minus 2t sine t minus cosine t. Oh man, I wish I hadn't started writing this. It's too late though. E to the minus 2t cosine t e to the minus 2t minus sine t minus cosine t. E to the minus 2t. I should have factored that stupid e to the minus 2t out front, you know? It's everywhere. We could have factored it out. Okay, so what we're looking at here is just x1 and x2. I mean, it's the two fundamental solutions concatenated into a matrix. That's all it is, okay? But that's a fundamental solution matrix. Okay. By the way, V equals to x times c vector is general solution. where here C is C1, C2. So like, if we have a fundamental solution matrix, we can express the general solution as the product of the fundamental solution matrix times the column vector of constants. It's another way of looking at things. So we could write down the fundamental solution matrix for example 5 as well, right? What would that be? So I actually have to kind of think through this. My A1 gives me cosine t here, and another minus cosine t in the third spot. The B's give me minus sine t here, and sine t down here. That's from those are the terms next to C1. For C2, we get sine where we had cosine before, and we get plus cosine where we had minus sine before. It's going to be a 4x4 matrix of functions. The third solution, built from it's got exponentials in it, right? So the third one's like e to the t, and I've got A2's got is e to the t cosine t. Yeah, and then let's see here, A2 e to the t cosine t minus e to the t sine t, I think. So minus sine t here. What's the third component? 0 cosines. I get 2 sines, but it's a minus 2 e to the t sine t. Well, let's see here. And for let's see here, sorry, I lost my place. Still working on the third one, which is here. Oh, I get e to the t minus 2 cosine t and minus 2 sine t, I think, yeah. All right, I'm tired of this. So, stuff. Okay, continuing this story, there's things that you can put there. If you look, again, this is number 11 from section 9.6. So the answer is actually in the back of the book. The rest of it, I'm just trying to show you where that comes from, okay? They present the answer as a fundamental solution matrix rather than as the general solution. So you say, like, well, what am I supposed to find? Am I supposed to find the general solution matrix, or am I supposed to find the general solution? Well, it depends on the question, right? I might ask you to find the fundamental solution matrix. I might ask you to find the general solution. I might ask you to find both. I don't know. Depends on my mood. Any questions? I'm tired of this 4x4 system. All right. So this one here, we'll do that one right quick here. So just go back up to my handy dandy calculator here. This one probably would be a decent, like, paper and pencil, or paper and pen question, whatever. The other one's kind of a bit much for an in-class test, but it might make a decent take-home problem, right? To give you guys interesting test questions for higher order systems, a lot of times what I'll do is I'll just give you sort of symbolic vectors and ask you questions about them. So we'll get back to that shortly here. So this one actually has a real eigenvalue of 0, and it has, that feels like the square root of 3, doesn't it? Yeah. Yeah, so it must be plus or minus root 3i. So if you don't mind, I'll just go ahead and write the solution down here for you. This one actually is mixed, right? We have one real eigenvalue and one complex conjugate pair, right? So and I'm glad we have inadvertently picked examples where beta was 1, right? But beta is often not 1, and so the arguments of cosine and sine have to be multiplied by a number as appropriate, right? So we've just kind of gotten either lucky or unlucky so far in that regard. So we have lambda 1 equals to 0 with u1 equals to what is it? So 1 minus 1, 1. That's my eigenvector, right? With eigenvalue 0. And then also lambda 2 equals, let's say, I times root 3. And then u2, what is it? With the plus root 3, 2. And then 1 plus root 3i. And then what's this? Minus 1 plus root 3i, right? So we got 2, 1 minus 1 plus I times 0 square root of 3 square root of 3, right? If I didn't misread it. Yeah. So far so good? All right, so what's the solution then? The solution is C1, 1 minus 1, 1. Where's my e to the t term there? Right, so the lambda 0, so e to the 0 t is e to the 1. I mean, is 1, right? Thank you. And then C2, and notice that this is pure imaginary, right? So we don't have an exponential term, we just have sines and cosines. So yeah, like C2 cosine square root of 3 t 2, 1 minus 1 minus the sine of the square root of 3 times t 0 root 3 plus C3 sine root 3 t 2, 1 minus 1 plus the cosine of the square root of 3 times t 0 root 3. And there you go. That's the general solution. Now, this is number 9, by the way, in section 9.6. So again, you can look in the back to check our answer. Now, when you do things numerically, it's not always possible to put it back in terms of square root of 3 or something, right? So as a general point of order, numerics in here, I like 3 decimal places. So like, you know, 1.732 is enough. You don't have to go past that. Every once in a while I find students who feel like obligated if the computer gives them 10 things past the decimal point that they have to keep them all. No, please no. On the other hand, 1.7, you know, that's enough that if you're doing something wrong, I might not be able to see it if you chop off too many. But usually 3 past the decimal point is almost always enough. 4 significant numbers is good, you know. I'm not too much of a stickler for all that. Anyway, any questions? Is clear? All right. All right, so let's look at my notes for a little bit because my notes have more examples. And let's see here. No. Where'd my stupid notes go? What? Oh, duh. It's right in front of me. Right, so let us peruse the notes and see what other, if you know, so, oh, that's right, I forgot. It's like light switches. Very exciting. I'm easily amused. Let's see here. So we've went through this today, right? This is a lot like our example 1. Distinct real eigenvalues. So we get distinct real eigenvalues in this example of 1 and -3. Eigenvectors 1, -5, 1, 1. So this gives us the general solution. There's the scalar solution if you like rip it off, x equals that, y equals that, right? This fundamental solution matrix in this case is this. It's e to the t minus 5, e to the t, e to the minus 3t, minus e to the minus 3t, okay? It's another example. This matrix is diagonal. It's kind of a silly case. When it's diagonal, then the whatever's on the diagonal are the eigenvalues. In fact, if the matrix is triangular, then whatever's on the diagonal are the eigenvalues. It's not hard to see why that is if you look at the characteristic equation, but there it is. So we get these eigenvectors 1, 0 and 0, 1, and those are my fundamental solutions. Fine. Still kind of in the basic case here. All right. Now this one is a little bit sort of more of a cautionary tale. Here we're going to start to get into trouble. We've got x prime equals to 3x plus y. Y prime equals to minus 4x plus y, right? It's second order problem. How many solutions should we find? 2. We go through the usual math. We calculate our characteristic equation. We get 1 repeated. But then when we go to find the eigenvector, we get 1, right? Any multiple of that, basically 1 minus 2 is my eigenvector. But this is a second order system. I mean, it's a system of two differential equations, right? We should find 2 fundamental solutions. We just found 1. Where's the other? Right? So you see there's something missing with this eigensolution technique that we have, right?
So even if it's the same solution, like, how to say, if it's the same thing, so like lambda minus 1 squared, you're going to find two different solutions, even though it's the same.
Well, the one right before this, we found, the one right before had minus 3 repeated, and we did find 2 eigensolutions for that one, because it was a diagonal matrix. But this one, we just find 1 eigensolution, so there's something missing. Like, this will not give us the general solution, it's just half of it. The reason for that is that this matrix is not diagonalizable. There's not enough eigenvectors to simultaneously like diagonalize this matrix. Okay. The algebraic multiplicity of 1 here is 2, but the geometric multiplicity is just 1 because there's just 1 eigenvector is another language you could use. So what do we need to do about that is the question, right? Here's a pretty standard complex example, 0 minus 1, 4, 0. This gives us characteristic equation lambda squared plus 4 equals 0, so lambda is plus or minus 2i. We find our single complex eigenvector, like so, rip off its real and imaginary parts, and go through the real part, imaginary part solution we just went through. All right, so the fundamental complex solution is this guy. We rip off its real and imaginary parts and build our general real solution down here like so. Again, here's the fundamental solution matrix. All right, so we've done these. Okay, good. Now, I'm not trying to say you understand it yet. You may or may not. I'm not sure where you are. You definitely need to do problems, right? Sorry to beat I know it gets old hearing me say it. That's part of the downside of the summer is like all of my nagging advice about studying, it all gets compressed. It's like every day, go do homework, go do homework. You know what you should do tonight? Homework. It's like same thing we do every night. Homework. So you like try to take over the world. Sorry, no, I'm not sure if Binky in the brain is widely known anymore. So this one, we get 2 plus or minus 3i for the complex solutions, which ends up giving us like e to the 2t cosine 3t and sine 3t type terms, right? And again, We find the complex eigenvector, we pick off its real and imaginary parts to get the A and the B, and that gives me these two fundamental solutions. All right, I'm kind of bored of this. Let's go on. I'm sorry. The moral of the story here is just that it's a 3x3 system. We have 3 distinct real eigenvalues. Good news, guys. Anytime you have an eigenvalue, you get at least one eigenvector. So like if you find distinct eigenvalues, good to go. It's diagonalizable. If I have a 3x3 matrix and its eigenvalues are 7, 8, 9, that means I can construct the general solution with eigensolutions. There will be enough eigenvectors. But it's when I have a repeated eigenvalue that there's trouble. Sorry. Good grief. How many examples do I have in these notes? What's the point of this example here? Let's see. It looks like we've got 2 repeated, right? And so in this case, we actually do get, as you can see here, we end up with 2 linearly independent eigenvectors corresponding to eigenvalue 2, which means that the geometric and algebraic multiplicity of 2 is both 2. Good news, we've got enough eigenvectors, so we get our general solution from the 1 eigenvector for 3, which is 0, 0, 1, and the 2 we found for 2 in here. This is much like example 2 today, right? This is it example 2? No, it's not example 2. But it's like example 2 from today. Here's another one. Now this one also has eigenvalue 2 repeated and eigenvalue 3 when you calculate the characteristic equation, right? And understand that there are details missing here, right? This is a 15-minute calculation or something, depending on how fast you are, right? I mean, that's a significant calculation. But anyway, so here's the subtracting the eigenvalue 2 equation. And look how the math works out. I actually have 2 distinct equations, right? In contrast to the previous example, there was just 1 equation after we simplified. This has 2 distinct equations. The one says v is equal to 0. The other one says that u plus w is equal to 0. So we just get 1 eigenvector with eigenvalue 2 in this example. So the algebraic multiplicity here was 2, but the geometric multiplicity is just 1 for eigenvalue 2. Now for 3, we get our token eigenvector. Great. But you see, we only have 2 eigensolutions here. This is a 3x3 problem. There should be 3 fundamental solutions. We're missing something, right? I hope I've convinced you by now we're missing something, right? Here's a stupid example. This is 7, 7, 7. So this is a diagonal matrix. The solution, I mean, this is just dumb. Whatever. It's just embarrassing. What's the point of this one? Here I have a eigenvalue minus 2 three-peated. Not a word, but you know what it meant. And when you look at the characteristic equation, you just get 1 equation, right? So how many eigenvectors do we get? If you look at it, we have 2 parameters, which speaks to the existence of 2 eigenvectors with eigenvalue 3. But again, we needed 3 to form the general solution set, so something's missing. All right? So the point of this these examples is to illustrate to you all of the different weird stuff that can happen with repeated eigenvalues. Right? You may or may not have as many eigenvectors as you have repeats in the characteristic equation. This one is, again, a 3-peated eigenvalue, but this time we just get 1 eigenvector. Right? Okay. Tons of possibilities is my point. All right? Let's see, what's this one? This is more or less like our example 6. It's a real with a pair with a complex. And all right, so finally. So guess what? The second path that we started to go down earlier today is what's going to save us. What's going to help us find the rest of the solution sets. all right? There is this thing called the matrix exponential.